In this question, we're asked to look at the relationship between kinetic and potential energy for a bicyclist as they move along a hilled path, if you will. So first they move down into a valley, up a little slope, down into a deep valley, and then up a large slope. So what we need to remember is that kinetic energy and potential energy must always sum up to be equal. So as the bicyclist moves down a hill, they convert some of their potential energy into kinetic energy. And then as they move back up the hill, they convert some of their kinetic energy into potential energy as their altitude increases. But at any given point, the total amount of kinetic and potential energy is the same due to something called the law of conservation of energy. And you might be wondering, why in a chemistry class am I considering a bicyclist moving up and down a slope? This should be reserved for a physics class. Because believe it or not, we use similar diagrams to this to explain how chemical reactions work, such as the chemical reaction that occurs in your engine that propels your car to go down the road. Let's go through each of these questions and answer them in terms of something that may be more familiar to all of us, bicyclists riding a bike, as opposed to what's going on in a combustion reaction inside of a car engine. Where would the bicyclist have the highest potential energy? Well, that would be the point at which his altitude was the highest. So here, F is the highest altitude, so therefore this is the highest potential energy, simply because it's the highest up. Where would the bicyclist have the lowest potential energy? That would be at the lowest altitude, so therefore this would be point D. Where would the bicyclist have the highest kinetic energy? Remember that kinetic energy is the energy of motion, and potential energy is the energy of position. So at the lowest point, the bicyclist would have the highest energy of motion, point D. Another way to think about this more practically is, where are you going to be going the fastest? His mass is going to be constant, so kinetic energy is going to be based on his speed. Well, when you get to the bottom of a hill on your bike, you're moving the fastest. Where would the bicyclist have the highest speed? We just answered that. That's point D. That's why his kinetic energy is the highest, because we assume his mass is a constant. Would the bicyclist have a higher bicyclist kinetic energy be higher at B or C? So here we have B and here we have C. Since C is higher in altitude, the potential energy, the energy of position, is higher for the bicyclist. Therefore, by definition, the kinetic energy must be lower. So the bicyclist would have higher kinetic energy at point B than at point C. Would the bicyclist's potential energy be higher at B or C? Well, this is exactly the opposite. Since C is higher in altitude, the potential energy is higher. So therefore, point C has a higher potential energy. Would the bicyclist's total energy be higher at B or C? Well, the law of conservation of energy says the bicyclist's total energy must always be the same. Said another way, energy cannot be created or destroyed. So here, the total energy is the same. And then the last question, suppose the bicyclist lets off the brakes and coasts down into the valley without pedaling. Even if there's no friction or air resistance to slow him down, what is the furthest point the bicyclist could reach without pedaling, without adding any additional energy? So here, if the bicyclist coasts down A and there's no friction or air resistance, they will come back to B, which is exactly the same amount of potential energy. So essentially, their kinetic energy is 0 if they're not moving. They start moving and coast all the way up to point B, where again, they stop moving, but their potential energy is equal. So they, in this case, would make it to point B. Notice that if point C were lower than it is, this bicyclist could, in theory, coast all the way to point E if there's no air resistance or friction. But because point C is higher in potential energy, the bicyclist can't overcome that. But if it were lower, like it is in some other examples, they may be able to coast all the way to point E.